High in the Chilean mountains, a camera the size of a car opened its eye for 10 hours. It found 2,104 asteroids nobody had ever seen. 7 of them cross Earth's path. Tonight we track a rock spinning once every 2 minutes, a visitor from another star, and the blind spot where the next impact will come from. Like and subscribe if you want to see what else is out there. Eyes open. We begin. The dome cracked open on a mountain in Chile, and for the next 10 hours nobody on that summit blinked. This was supposed to be a test. Engineers wanted to know if their new machine actually worked, so they aimed it at one crowded patch of sky and let it run. Picture after picture of the same region, again and again. Like a security camera watching a parking lot waiting for something to move. Then they looked at what came back. 2,104 asteroids. Every single one of them new. Every single one of them unknown to every catalogue, every database, every astronomer on the planet until that week. Sit with that for a second. Every asteroid humanity had ever found before that night was found the hard way. Someone stared at a photographic plate. Someone compared 2 images by hand. Someone argued with a colleague about whether a smudge was real. That work took 200 years. This machine did a chunk of it before the sun came up. And buried inside that swarm of 2,000 rocks were 7 that mattered more than the rest. 7 objects whose orbits bring them into our neighbourhood. 7 that cross the same stretch of space we travel through every year. None of them are coming for us. The scientists checked that first, and they checked it carefully. But here is the part that should make your stomach drop. Those 7 were sitting there the whole time, circling the sun, sweeping past Earth's orbital lane, completely invisible to us, because until that week we had never built an eye sharp enough to catch them. They were only found because someone was testing the equipment. The telescope is called the Simony Survey Telescope, and it sits inside the Vera Rubin Observatory, high on a ridge in the Chilean Andes. It cost around $470 million. It took decades to design, and on the day the team released those first pictures to the world in a room in Washington, the asteroids were almost an afterthought. The headline images were the pretty ones, glowing clouds of gas where stars are being born, a single frame containing 10 million galaxies, each one holding hundreds of billions of suns. Then they played a short video, 1,185 frames stitched together. Against a frozen background of stars, dozens of tiny dots crawled across the screen in different directions, at different speeds, like insects on a window pane. Astronomers in the audience described the feeling as emotional, strange for a room full of scientists watching white specks. But they understood what they were seeing. Each of those specks was a mountain of rock, miles from anything, older than the Earth itself, and it had just been discovered in front of them in real time. One researcher summed up the whole project in a single sentence. He said this observatory could outdo 2 centuries of effort in a couple of years. That is the promise. A complete headcount of the solar system. Every rock, every comet, every drifting shard left over from the day the planets formed. And a complete headcount means something uncomfortable. It means we are about to learn exactly how many objects are out there with our name written on their orbit. For now, though, the question is simpler. How does a machine find in 10 hours what took the rest of us 200 years? The answer starts with a piece of glass that had to be melted while spinning. To catch something faint, you need a bucket. To catch something very faint, you need a very large bucket. Light behaves a little like rain. A raindrop lands wherever it lands, and if you want to collect a lot of rain quickly, you widen the container. Starlight works the same way. Photons from a distant asteroid arrive scattered thinly across space, and a telescope mirror is a bucket that gathers them into one point. The mirror at the heart of this observatory is 27 feet across. Stand it upright and it would fill the front of a 2-story house. That size alone would make it impressive. What makes it strange is the shape. Most large telescopes use 2 mirrors, a big one at the bottom to gather light, a smaller one up top to bounce it back down toward the camera. Simple, proven, used for a century. This one uses 3, and 2 of those 3 are carved into the same single piece of glass. Picture a satellite dish. Now imagine that in the middle of that dish someone has ground out a second, tighter curve, a shallow bowl sitting inside the larger bowl. 2 different optical surfaces, 2 different jobs, 1 slab of glass. Light falls onto the outer ring first, 27 feet wide. It bounces upward to a secondary mirror suspended above, 11 feet across. That mirror throws it back down onto the inner bowl, which finally aims it into the camera. 3 bounces in a space barely longer than a school bus. Why go to all that trouble? Because folding the light path that many times lets the designers do something no other giant telescope can do. It gives them an enormous field of view without blurring the edges. Most big telescopes see the sky through a keyhole. They are built to stare hard at one tiny target, which is perfect if you already know where to look. This machine was built for the opposite problem. It had to cover ground. The glass itself was born in a furnace at the University of Arizona, spun like a merry-go-round while molten so that the liquid surface naturally curved into shape as it cooled. It weighs more than a truck. It sits on a bed of pistons that push and flex it constantly, correcting for the sag of its own weight as the telescope tilts. Then came the polishing. The finished surface is smooth to within a fraction of the wavelength of light. Scale that mirror up to the width of the United States, and the tallest bump on it would be a few inches high. All of that engineering exists to serve one purpose: depth. A rock a few hundred feet wide drifting somewhere past the orbit of Mars reflects a pitiful amount of sunlight back toward us. It is charcoal dark, freezing cold, and unimaginably far away. To most telescopes it does not exist at all. To a 27-foot bucket it is a faint but real signal, and if you photograph it enough times it becomes a track. There is a catch though. Gathering the light is only the first half of the machine. The mirrors deliver a flood of photons to a single focal point, and something has to be sitting there to record them. Whatever sits at that point has to be wide enough to capture the whole field, sensitive enough to register a handful of photons, and fast enough to do it every 40 seconds all night long. Nothing like that existed, so they built it, and it turned out to weigh 3 tons. They wheeled it into the dome in a custom crate, off a cargo plane, up a mountain road, and every person watching knew that if the truck slipped, 20 years of work went off a cliff. The camera at the heart of this telescope is the largest digital camera ever built. It is roughly the size of a small car and weighs more than 3 tons. The phone in your pocket has a sensor smaller than a fingernail. This one has a light-collecting surface the width of a dinner plate, assembled from 189 separate chips fitted together like tiles on a bathroom floor. Add up all those tiles and you get 3,200 megapixels. Numbers like that go numb fast, so try it this way. To display one single image from this camera at full resolution, without shrinking anything, you would need a wall of about 370 high-definition televisions. One picture, 370 screens, and it takes a picture like that every 40 seconds or so, all night, every clear night for 10 years. Each of those shots covers a patch of sky about 45 times the area of the full moon. Hold your hand up at arm's length and cover the moon with your fingertip. Now imagine capturing an area of sky the size of your whole palm, in perfect focus, right out to the corners, with every star and galaxy and drifting rock recorded at once. The tiles themselves had to be assembled in a clean room by technicians moving at a crawl. The gaps between neighbouring chips are thinner than a human hair, and the entire surface had to be flat to within a fraction of that. A single dropped screwdriver would have ended careers. Then there is the cold. The sensors run at about 170 degrees below 0 Fahrenheit, kept there by a refrigeration system that never stops. Warm electronics generate their own faint glow, a kind of electrical static that would drown out the whisper of light coming from a distant asteroid. Freeze them, and the static dies away. In front of the sensors sit 6 enormous glass filters, each one a coloured lens the size of a manhole cover, swapped in and out by a robotic arm. One filter passes blue light, another passes red, another reaches into the infrared, past what human eyes can register. Those filters are the reason this machine can tell you what an asteroid is made of. Photograph the same rock through different colours and compare how bright it looks in each one, and the pattern reveals its surface. Iron reflects differently than carbon. Rock differs from ice. So the camera is doing 2 things at once. It finds the object, and it fingerprints it. Every exposure pours about 20 terabytes of data down the mountain each night. Over the full decade, the archive will grow to around 500 petabytes, a number so large that the observatory had to design its own data pipeline before it ever ground a lens. Which brings us to the actual trick, because a photograph of the sky, no matter how sharp, does not show you an asteroid. It shows you a field of dots. Stars are dots. Galaxies are dots. Cosmic ray hits are dots. Dead pixels are dots. Somewhere in that mess of millions of points of light, a few are moving. Finding them requires a piece of software that does something almost absurd. It takes the sky and it subtracts the sky from itself. Here is the problem in one sentence. An asteroid looks exactly like a star, except that it is in a slightly different place tonight. That is the entire difficulty of the hunt. Rocks in space do not glow. They reflect a little sunlight. They appear as faint smudges, and they sit in a photograph next to thousands of other faint smudges that are actually distant suns. The only thing that gives them away is motion. So how do you spot motion in an image containing millions of objects taken 40 seconds ago when you have another image arriving in 40 more? You cheat. You subtract. The observatory keeps a reference picture of every patch of sky it covers, built by stacking earlier images into one clean, deep template. When a fresh photograph comes in, the software lines it up against that template pixel by pixel and takes the difference between the two. Everything that stayed put cancels out. A star that was there last month and is there tonight subtracts to nothing. A galaxy subtracts to nothing. The faint glow of dust in our own Milky Way subtracts to nothing. What remains is a black frame with a few bright dots floating in it. Anything that changed, anything that moved. It works like a spot the difference puzzle, except the software does not compare the two pictures side by side. It presses them together and lets them erase each other, leaving only the mismatch behind. Those leftover dots come in two flavors. Some things change brightness while staying in the same spot, which usually means a star exploding or a black hole tearing something apart. Other things appear in one place, then reappear a little further along in the next exposure, then further again. Draw a line through those positions and you have a track. Feed the track to an orbit solver and you get a path around the sun. Send that path to the world's asteroid clearinghouse, and if nobody has seen it before, a new object joins the catalogue. The difficulty hides in the details. Two photographs of the same star field never match perfectly. The air above the telescope wobbles, so one image is slightly blurrier than the other. The tracking shifts by a hair. A satellite draws a streak through the frame. A cosmic ray strikes the sensor and leaves a hot pixel that looks convincingly like a distant world. Each of those glitches survives the subtraction and pretends to be a discovery. So the software has to be ruthless. It weighs shape, brightness, and consistency and throws out anything that fails. The teams that built these pipelines, many of them working at the University of Washington, spent years teaching machines to distinguish a real moving rock from a smear of noise. When it works, the result is beautiful. In that first 10-hour test, the pipeline pulled out just under 4,000 moving objects from a single field. Roughly 1,800 of them were already known. The rest were new. More than half the objects in that patch of sky had been invisible to us. That is the discovery that should worry you slightly. The sky was already full. We simply lacked the eyes. And when the team coloured the moving dots by category and pressed play on that video, most of the specks drifted slowly, in a lazy shared direction. 7 of them tore across the screen. In the video, they are the wrong colour. Everything else drifts in white and blue. 7 objects burn orange, and they cross the frame so quickly that your eye follows them without being told to. Speed on that screen means one thing: closeness. Think about riding in a car. A distant mountain on the horizon barely shifts as you drive. A fence post beside the road whips past your window in an instant. Both are standing still. The difference is how far away they are. Space works the same way. An asteroid out beyond Mars, 300 million miles from here, crawls across a telescope image over hours, a rock passing through our own neighbourhood streaks. Those 7 orange dots were near-Earth objects, bodies whose orbits carry them into the region of the solar system where we live. 7 in one test, in one small patch of sky, on the first serious night of operation. The team stressed immediately that none of them threatened anything. Their orbits were calculated, checked and cleared. They will pass by, as countless objects do, and we will never feel them. But their discovery told astronomers something they had suspected for years and could finally measure. The neighbourhood is more crowded than our maps show. Here is why they were missed for so long. A near-Earth asteroid a few hundred feet across, made of dark rock, reflects less light than a lump of coal. When it is far from us, it is invisible. When it comes close enough to reflect a decent amount of sunlight, it is also moving fast enough that older survey telescopes struggle to catch it. In the time it takes some observatories to gather enough photons for a solid detection, the object has already smeared itself across the exposure. You need two things at once: a wide gaze and a fast shutter. Almost every telescope ever built forced astronomers to pick one. This one refused to choose. Its enormous mirror gathers light fast enough to freeze the motion, and its enormous camera keeps the whole field in frame while it happens. The result is a machine that finds exactly the objects we have been worst at finding: small, dark, quick, and close. There is a detail in that first release that deserves a moment. Alongside the 7 near-Earth objects, the survey pulled out 11 Trojan asteroids sharing Jupiter's orbit, locked in gravitational pockets ahead of and behind the giant planet, and 9 bodies out beyond Neptune in the frozen outer dark. One patch of sky, of 3 completely different populations at wildly different distances, all captured in the same set of frames. The inner solar system, the middle and the far edge, photographed simultaneously by accident. That is what a survey telescope means. It does not go looking for one thing. It records everything that happens to be in the way, and scientists mine the result for decades afterward. Which raises a fair question. Astronomers have been hunting asteroids seriously since the 1990s. There are dedicated survey programs in Hawaii, in Arizona, in Chile, in space. Thousands of new rocks get logged every year by teams who have spent their careers on this. How much of a difference does one telescope really make against all of that combined effort? The honest answer arrived when someone did the arithmetic, and it made a lot of veteran asteroid hunters go quiet. Every year, all the asteroid hunters on Earth put together find about 20,000 new objects. That figure includes the automated sky patrols in Hawaii, the survey telescopes in the Arizona desert, the network of alert scopes scattered across 4 continents, the amateurs with backyard rigs and enormous patience, and the space-based hunters watching in infrared. Add up an entire planet's worth of professional and volunteer effort for 12 months, and you get 20,000. The new observatory in Chile is expected to reach that figure in a couple of nights, not by being cleverer, by being relentless. The difference comes down to a concept astronomers call grasp. Take how much light a telescope can gather, multiply it by how much sky it can see at once, and you get a single number describing how quickly it can survey the universe. This machine's grasp beats every other optical telescope ever built by a wide margin. The estimates for what happens next are the kind of thing scientists usually hedge on. Here, they barely bother. Over the coming decade, this survey should roughly triple the total number of known asteroids in the solar system. Everything found by everyone, ever, since an Italian monk spotted the first one on the opening night of the 19th century, will become a minority of the catalogue. In the first year alone, researchers expect around 1 million new discoveries. That single year matches what humanity managed in the previous 200. Numbers this large stop meaning anything, so anchor it. Imagine every asteroid ever discovered represented by 1 grain of rice. You would have a couple of large sacks. Now imagine the survey's 10-year haul poured out beside it, filling the room to your knees. The scale changes what questions you can even ask. With a small sample, you study individuals. This asteroid is unusual. That one has a strange colour. With millions, you study populations. You can ask why families of rocks cluster at certain distances, whether there are missing size ranges that hint at ancient collisions, how the belt has been shepherded and stirred by Jupiter over billions of years. You stop reading single sentences and start reading the whole book. And there is a colder application. When you know where nearly everything is, you can calculate where nearly everything will be. Orbits get propagated forward, decade by decade, and the software flags anything whose future path threatens to intersect ours. A complete census turns planetary defense from a guessing game into bookkeeping. That is the promise anyway. Getting there requires the survey to run for years, and to run well, which is why the whole enterprise carries the weight of an entire scientific field on its back. It also carries a name. The observatory could have been named for a donor or a politician or a president. Instead, it carries the name of an astronomer who spent years being told, politely and repeatedly, that her measurements had to be mistaken. She was not measuring asteroids. She was measuring how galaxies spin, and the numbers she kept getting made no sense. Either her instruments were broken, or roughly 80% of the universe was made of something nobody could see. She wanted a career in astronomy at a time when the field made that difficult on purpose. Vera Rubin applied to graduate school at Princeton in the 1940s and was told the astronomy program did not accept women. She went elsewhere. When she wanted to observe at Palomar, one of the great telescopes of the era, the facility had no women's restroom, a detail that had been used for years as a reason to keep the mountain closed to her. In 1965, she became the first woman granted official observing time there. The story goes that she taped a paper skirt onto the drawing of a figure on a door and got on with her work. What she chose to work on seemed almost boring at the time. She measured how fast the outer regions of galaxies rotate. Everyone already knew the answer, or thought they did. A galaxy is a swirl of stars orbiting a bright, dense centre, and that arrangement should behave like the solar system. Mercury whips around the Sun in 88 days. Neptune takes 165 years. The further out you go, the slower you move, because the gravitational grip of the centre weakens with distance. Galaxies should do the same. Fast in the middle, sluggish at the edges. Working with a colleague named Kent Ford, using a sensitive instrument he had built, Rubin measured the spin of the Andromeda Galaxy, then dozens more. She looked at the stars way out on the lonely fringes, where the light thins into darkness. They were moving just as fast as the stars near the core. Picture a carousel spinning up. The horses near the centre rotate calmly. The ones on the outer rim swing around at high speed. Now imagine standing back and seeing every horse, inner and outer, moving at exactly the same rate, as though the whole thing were welded to a solid disk. That is what galaxies do. And by the ordinary rules of gravity, those outer stars should have been flung into intergalactic space long ago. The only way to hold them in place is to surround the galaxy with far more mass than the glowing parts contain. A vast invisible halo, gripping everything with its gravity, giving off no light whatsoever. Rubin's galaxies, one after another, all said the same thing. She kept measuring. The pattern kept holding. Her data turned an oddity that a few theorists had toyed with into a fact the field could not walk around. Most of the universe is made of something we cannot see, and everything we can see, every star and planet and person, floats inside it like foam on a dark ocean. She never received a Nobel Prize. She died in 2016. The observatory carries her name because its main scientific mission is to map that invisible material by watching how it bends light across billions of galaxies. Asteroids are technically a side effect, which is a strange thought. The most powerful tool ever built for finding rocks that might hit Earth exists mainly because someone wanted to understand what holds galaxies together. But no instrument, however brilliant, works from just anywhere. Point it through the wrong patch of air and every image turns to mush. Finding the right mountain took its own years of searching, and the winning ridge sits in a desert where it sometimes goes a decade without meaningful rain. Look up on a clear night and stars twinkle. Poets love it. Astronomers hate it. That shimmer has nothing to do with the star. It happens in the last few miles of the journey, when starlight that has travelled undisturbed for thousands of years finally hits our atmosphere and runs into pockets of warm and cool air stacked on top of each other. Each pocket bends the light slightly differently, and it bends differently every fraction of a second. The result is a smeared, dancing blob where a sharp point should be. Astronomers call the effect seeing, and it is the single biggest limit on ground-based telescopes. You can build the most perfect mirror in history and still get mush if the air above it is churning. So the search for a sight becomes a search for stillness. The observatory sits on Cerro Pachon, a ridge in north-central Chile, at roughly 8,900 feet. Nearly 3,000 feet of the atmosphere's densest, most turbulent layer already lies below you at that height. The location was chosen for a stack of reasons that all point the same direction. The Chilean coast is bordered by cold ocean water that suppresses cloud formation, and by the Andes, which wring moisture out of the air before it can reach inland. What is left is a desert so dry that some weather stations there have recorded no significant rainfall for years at a time. Dry air means fewer clouds, and water vapour also absorbs the infrared light astronomers want. Steady winds off the Pacific arrive smooth rather than churning, flowing over the ridge in a laminar sheet, which keeps the air above the dome unusually calm. The nearest large city is far enough away that its glow stays low on the horizon. Chile has taken this seriously enough to write light pollution rules protecting its northern skies, because those mountains have become one of the most valuable pieces of astronomical real estate on the planet, and it looks south. That matters more than it sounds. The centre of our own galaxy, the Magellanic Clouds, and huge stretches of sky that northern observatories never see are all southern targets. Even the building itself fights the enemy. The dome is designed to flush air through it during the night so that the interior matches the outside temperature. A telescope warmer than the air around it creates its own private heat shimmer, ruining images from inside the very structure meant to protect it. So the whole facility breathes. The mirror gets stripped and recoated with a layer of aluminum only a few hundred atoms thick, a job that requires lifting the glass out of the telescope entirely and treating it like a patient in surgery. All of it exists to protect a few photons, and once you have a perfect mountain, a perfect mirror, and a perfect camera, one problem remains, and it is the one nobody expected to be hardest. You have to point the thing, because a telescope that photographs the entire visible sky every few nights cannot afford to spend a leisurely minute swinging between targets. It has to whip a structure heavier than a loaded truck across the sky, stop it dead, and hold it steady enough to capture a rock 1 billion miles away. It does that in 5 seconds. The dangerous part of an earthquake for a telescope is not the shaking, it is the settling afterward. Move any large structure quickly, and it does not stop where you tell it. It overshoots, springs back, and vibrates like a struck tuning fork. For most giant telescopes, this is a minor annoyance because they spend hours locked onto a single target anyway. Point once, then sit. This machine cannot sit. Its entire mission depends on covering ground. To photograph the whole visible southern sky every 3 to 4 nights, it has to take somewhere around 1,000 exposures per night, which means it repoints roughly 1,000 times before sunrise. If each move wasted a minute, most of the night would vanish into aiming. So the engineers built a telescope that moves like an athlete instead of a monument. The trick is shape. Traditional big telescopes are long tubes, tall and narrow, which makes them top-heavy and slow to swing. Folding the light path across 3 mirrors let designers collapse the whole optical assembly into something short and squat, closer to a barrel than a cannon. A compact shape means less leverage fighting the motors and less wobble at the end of a move. Then they mounted the entire assembly on a system that floats it on a thin film of oil under pressure, so that hundreds of tons of steel and glass ride almost without friction. Powerful motors accelerate it, then brake it hard, and active damping absorbs whatever ringing is left. From the end of one exposure to the start of the next, the whole structure swings to a new patch of sky and stabilizes in about 5 seconds. No telescope of comparable size comes close. Think of a battleship gun turret performing ballet. That speed unlocks the science, because finding an asteroid once is nearly useless. A single detection gives you a dot, 2 detections give you a direction. To pin down an actual orbit, you need the object caught repeatedly, across nights and weeks and months, so the software can fit a curve through the solar system that satisfies every observation. Over the full survey, each point on the southern sky gets photographed roughly 800 times. Every rock that wanders through gets caught again and again, and each new sighting tightens its predicted path. That repetition is the difference between knowing an asteroid exists and knowing where it will be in 20 years. There is a bonus buried in the design. Because the sky gets revisited every few nights, the survey does not only find things that move, it finds things that change, stars that flare, distant explosions that brighten over a week and fade over a month. objects that vanish entirely. The universe turns out to be restless on timescales we have never systematically watched, all of which creates a new and slightly ridiculous problem. A machine photographing the entire sky every few nights, comparing every image against a reference, and flagging every difference, generates a flood of notifications about changes in the universe. The flood is not thousands per night. It is not tens of thousands. On a working night, this observatory can throw off up to 10 million alerts before sunrise, and every single one of them is published to the entire world within about a minute of the photon's landing. No human being will ever read them. Data leaves the mountain at the speed of light, down a fibre optic line strung across 2 continents. Every image the camera takes gets processed almost immediately. The software compares it against the reference sky, isolates whatever changed, and packages each change into a small bundle of information called an alert. Position, brightness, colour, a set of cut-out images, and a history of everything previously seen at that spot. Then it publishes. The target is to get each alert out to the world within about 60 seconds of the shutter closing. On a busy night, the stream can reach millions of alerts. During commissioning, one single night produced around 800,000 flag changes in the sky, and that was the system warming up. The whole night's data haul runs to roughly 20 terabytes. Over 10 years, the archive grows to about 500 petabytes, which would fill millions of ordinary laptops. Confronting a stream like that, the old way of doing astronomy simply breaks. For 400 years, discovery worked like this. A person looks, a person notices, a person decides it matters. Every stage runs at the speed of human attention. 10 million alerts a night destroys that model completely. If you spent 1 second glancing at each alert, working without sleep, you would fall behind by weeks after a single night of observing. So the alerts go to machines. Independent teams around the world run what are called brokers, systems that drink from the fire hose and sort it. They filter by object type, by brightness, by location, by rate of change. An astronomer studying stellar explosions in nearby galaxies sets up a request, and their broker delivers only the handful of events matching it, out of millions. The filtering happens in near real time, which changes what is possible. Some of the most interesting things in the universe last hours: a star's outer layers being blasted off, the first flash from a collision between dead stellar cores, a distant sun being torn apart as it falls into a black hole. Traditionally, by the time anyone noticed such an event in the data, the moment had passed and only the aftermath remained. Now the alert arrives while it is still happening, and other telescopes can be turned toward it that same night. For our purposes, the important stream is the moving one. Objects that shift position between exposures get funneled towards solar system processing, where their tracks get linked across nights, converted into orbits, and reported to the international body that keeps the master catalogue of small bodies. That handoff is where discovery becomes official. And it is where a subtle problem surfaced, one that nobody outside the field would ever have guessed mattered. When the team compared their measured positions of objects against the existing reference catalogues the whole world uses, they found a mismatch. Small, consistent, systematic. Everyone's asteroid positions were off by the same tiny amount in the same direction. The size of the error is almost comically small, yet planetary defense runs on exactly this arithmetic, projecting orbits forward for decades, and a systematic error that appears in every single measurement does something that random noise never does. It accumulates. Aim a rifle at a target 100 yards away and tilt the barrel by the thickness of a sheet of paper. At that distance, the shot still lands close. Now imagine the target is a mile away, then 10 miles. The tilt never changed. The miss grew. That is the shape of the problem the survey uncovered in the world's asteroid catalogues. To calculate an orbit, you need to know precisely where an object appeared in the sky at a precise moment. Precisely means measuring the angle to a startling degree of accuracy. Astronomers work in arc seconds, and 1 arc second is roughly the width of a penny seen from 2.5 miles away. They then subdivide that into thousandths. When this observatory compared its own measurements against reference positions used across the field, it found an offset of about 20 to 40 of those thousandths. Take that penny 2.5 miles away, and the error is a small fraction of its width. utterly invisible in any single observation, buried far below the noise of ordinary measurement, but it is a bias rather than a wobble. Random errors cancel out when you average many measurements together, which is why astronomers take many. A bias points the same way every time. Average 1,000 of them, and the bias survives untouched. Now feed that into a planetary defense calculation. To decide whether an asteroid threatens Earth, software takes its observed positions, fits an orbit, and runs that orbit forward through time, often for 50 or 100 years. Gravity from the Sun, from the planets, even the faint push of sunlight on the rock itself will get folded in. A tiny consistent error in the starting position becomes a large error in the predicted destination, because the mistake gets multiplied by every year of travel. Practically, this shows up as uncertainty in something called the impact corridor. When an object has a small chance of hitting us, astronomers calculate a cloud of possible future positions. Earth either sits inside that cloud or outside it, and the size of the cloud determines whether a possibility is a scare or a crisis. Sharpen the input measurements, and the cloud shrinks. Shrink the cloud enough and possibilities resolve into certainties, one way or the other. The fix is already coming from the same telescope that found the problem. By imaging the southern sky hundreds of times with a single consistent instrument, the survey is building a reference catalogue of star positions more accurate than anything that existed before, and that catalogue becomes the ruler everyone else measures against. Within roughly a year of full operation, the whole field gets a better foundation underneath it. There is something quietly humbling in that. The most sophisticated planetary defense calculations on Earth were resting, without anyone realizing, on a ruler that was slightly warped. Meanwhile, the telescope kept observing. The test images were over. The team moved into a phase they called optimization, tuning the survey strategy, learning how the machine behaved on real sky night after night. They ran that phase for about 6 weeks, and when the solar system team finished processing what those 6 weeks contained, the number they had to submit to the world's asteroid clearinghouse was large enough that it caused a backlog. There is an office that keeps the master list of every small body in the solar system, every asteroid, every comet, every icy fragment beyond Neptune. Discoveries from every observatory on Earth funnel into it, get checked, get cross-referenced against everything already known, and get assigned a designation. The Minor Planet Center has been doing this for decades. It handles a steady flow. Then this observatory submitted the results of 6 weeks of tuning, more than 11,000 new asteroids in one batch. It was the largest single set of discoveries submitted in the previous year from anyone, anywhere, and it came from a telescope that had not officially started its main survey yet. The team was blunt about what it represented. One of them called it the tip of the iceberg. That phrase deserves unpacking, because the arithmetic behind it is genuinely startling. Those 11,000 objects came from 6 weeks of intermittent, imperfect, still being adjusted observations. Once the full 10-year survey runs properly, scientists expect the machine to produce a comparable haul every 2 to 3 nights during the early years. The bottleneck stops being the telescope. It becomes everything downstream. Look at how the discoveries piled up over time, and the acceleration becomes obvious. During the earliest engineering tests in late 2024, using a smaller commissioning camera, the count was 73. During the first look observations the following spring, it reached about 1,500. Then the optimization surveys added 11,000. 73, then 1,500, then 11,000. The curve bends sharply upward, and the discoveries themselves were only half the value. The same data produced better orbits for tens of thousands of asteroids that were already known but poorly tracked. That second contribution rarely makes headlines and matters enormously. A known asteroid with a sloppy orbit is a liability. It has been seen a handful of times, its path is a rough estimate, and it can drift away from where the catalogue says it should be until nobody can find it again. Astronomers call these objects lost. Every high-quality observation drags a wobbly orbit towards certainty. So the survey does 2 jobs at once. It floods the catalogue with the new entries, and it repairs the entries that were already there. Verification matters too. When the Minor Planet Center confirms a batch, the data goes public immediately, and researchers everywhere can start refining orbits and hunting for these objects in old archives. Sometimes, a newly discovered rock turns up in photographs taken years earlier by a completely different telescope, and suddenly its orbit is nailed down across a decade instead of a week. The system feeds itself. Among the 11,000, most were ordinary residents of the main belt between Mars and Jupiter, drifting harmlessly in the gap where a planet failed to form. Hundreds were something else entirely, out in the frozen dark past Neptune, and we will come back to them. But 33 of them belong to a category that gets a different kind of attention. 33 came home with us into the same stretch of space Earth occupies. 33 in 6 weeks. And the word astronomers use for that category has a meaning far looser than it sounds. The phrase near-Earth object sounds like something skimming the rooftops. The official definition is considerably more relaxed. An object qualifies if its orbit brings it within about 28 million miles of the Sun at its closest approach, which means its path wanders into the general region of the inner solar system where Earth lives. That is more than 100 times the distance to the Moon. So near means something closer to in the same district than in the same room. Of the roughly 40,000 such objects catalogued so far, the overwhelming majority will never come anywhere near us. They cross our orbital neighbourhood on their own schedule, and Earth is a small target moving fast. A smaller group earns a sharper label. To be called potentially hazardous, an object has to satisfy 2 conditions at once. Its orbit must come within about 4.5 million miles of Earth's orbit, and it must be large enough to survive the atmosphere and do serious damage on the ground. Note the careful wording there. The distance is measured between the 2 orbital paths, rather than between the 2 bodies. 2 racetracks can nearly touch while the cars on them stay far apart for centuries. The label is about geometry and possibility, and it flags which objects deserve watching over long spans of time. The reason this bookkeeping matters comes down to how orbits behave. An asteroid does not travel a fixed loop forever. Every close pass by a planet tugs at it. Jupiter shoves things around from a distance with enormous authority. Sunlight itself exerts a faint pressure that, over millions of years, can nudge a rock's path measurably. Orbits drift. Objects migrate. Something that poses no risk this century can be steered into a different situation over long enough timescales. Which is why finding 33 previously unknown near-Earth objects in 6 weeks of test observations landed the way it did. None of them threaten us. That gets checked immediately, and it gets checked well, but their existence confirms what the models predicted. There is a substantial population of these objects still hiding, and they are hiding for a specific reason. They are small. The big ones are largely accounted for. Objects wider than about 6/10 of a mile, the true civilization enders, have been hunted since the 1990s, and astronomers have found well over 90% of them. Those are bright enough and slow enough to be caught with older equipment. The population grows steeply as size shrinks. For every giant there are many mid-sized objects, and for every mid-sized object thousands of small ones. And smaller means fainter, which means harder, which means missed. Once the full survey runs, this observatory alone is expected to find roughly 90,000 additional near-Earth objects. Some fraction of those will carry the hazardous label. Now, 90,000 new objects sounds terrifying until you remember that every one of them was already out there. Discovery changes nothing about the sky. It changes what we know about the sky. The uncomfortable part is what the current numbers imply about the middle of the size range. There is a specific width where astronomers stop worrying about light shows and start worrying about cities. That threshold is about 460 feet, and we have found fewer than half of them. Somewhere between a pebble and a mountain sits a size where an asteroid stops being a spectacle and starts being a disaster. Astronomers draw that line at roughly 460 feet across. Picture a rock as wide as a 40-story building is tall, tumbling through space at tens of thousands of miles per hour. Objects that size get special attention for a reason grounded in physics. Everything falling toward Earth hits the atmosphere at enormous speed, and the atmosphere fights back hard. Air cannot get out of the way fast enough, so it compresses in front of the object, heats to thousands of degrees, and starts stripping it apart. Small rocks lose this fight entirely. Several tons of material burn up over your head every single day and you never notice. Bigger objects survive longer, penetrate deeper, and release their energy lower down. The energy involved comes from speed rather than mass. Kinetic energy scales with the square of velocity, so doubling the speed quadruples the punch. A typical impactor arrives somewhere around 11 to 25 miles per second, which is faster than a rifle bullet by a factor of 30 or more. At those speeds, ordinary rock behaves like a bomb. Below a few tens of feet, you get a bright fireball, and maybe some meteorites for collectors. Around 100 feet and upward, you get an airburst capable of shattering windows across a region. At 460 feet, the physics changes character. An object that large carries enough energy that a strike on land would devastate an area comparable to a small country's worth of populated territory, and an ocean strike could generate destructive waves across a coastline. The United States Congress found this compelling enough to write it into law. Around 2005, they directed the space agency to find 90% of near-Earth objects at or above that size. The reasoning was simple. Objects large enough to end civilization are rare and mostly already found. Objects small enough to burn up are common and mostly harmless. The 460-foot range sits at the intersection of common enough to happen and large enough to ruin a region. It is the sweet spot of danger. Now put that alongside how often such things arrive. Objects in this class strike Earth on average every several thousand years, which sounds comfortable until you notice that averages say nothing about timing. A once-in-a-few-thousand-years event has the same chance of happening this decade as any other. We simply have no idea because we have no complete list. And that is the actual problem. The threat is manageable, the physics is understood, the technology to respond exists in early form. The missing ingredient is the inventory. 2 decades after that law passed, with dedicated surveys running the whole time, astronomers have found somewhere around 40% of the objects in that dangerous size class. 40%, which means that for every city-sized threat we have catalogued and can predict, there are roughly 1.5 more we have never seen, tracing paths we have never measured, on a schedule nobody has calculated. The question is what the missing majority looks like, and why 2 decades of hunting has failed to find them. Imagine a room containing 100 people, and you can only identify 40 of them. The other 60 are in the room with you. They have always been there. You simply cannot make out their faces. That is the current state of our asteroid census in the dangerous size range. The reasons for the gap are boring, which somehow makes them worse. Start with brightness. An asteroid shines only by reflected sunlight, and the light we receive drops off brutally with distance. It weakens on the way out to the rock and weakens again on the way back. Combine those and a rock twice as far away appears about 16 times fainter. Now shrink it. Halve the diameter and you quarter the surface reflecting light. A small dark object far from the sun is a spectacularly difficult target. Then there is colour. Many asteroids are extraordinarily dark. Some reflect only a few % of the light hitting them, which is darker than fresh asphalt and comparable to charcoal. Space weathering does this, baking surfaces over hundreds of millions of years until they turn sooty. A charcoal rock against a black sky, seen from millions of miles away, is close to the definition of invisible. Speed compounds everything. Objects that come near us move quickly across our field of view, so a long exposure smears them into a faint streak instead of building a solid point of light. Older survey telescopes had to choose between depth and sharpness, and either choice lost objects. Geography finishes the job. Most large survey telescopes historically sat in the northern hemisphere, which left the southern sky comparatively thinly patrolled for decades. Put those together and a clear picture emerges of what our catalogue is missing. Small, dark, fast, southern, which is a fairly exact description of what this new observatory was designed to catch. Once the survey matures, projections suggest it will lift completeness in that critical size class from around 40% to roughly 70%, not perfection. A dramatic improvement over a single decade, achieved by one machine. Getting the remaining 30% requires a different approach entirely, and there is a spacecraft being built for exactly that job. We will come to it. For now, hold on to the shape of our ignorance, because history has already shown us what it feels like when the unseen majority sends a representative. Twice in living memory, an object arrived that nobody had catalogued, nobody had tracked, and nobody saw coming. In both cases, the world found out when the sky lit up. The first happened in a place so remote that scientists did not reach the site for nearly 20 years. It flattened a forest larger than a major metropolitan area and left behind a mystery that took a century to fully settle. The second happened above a city of more than 1 million people on a Friday morning with dashboard cameras running. Both objects were small enough to fall well below the threshold we have been discussing. Neither of them touched the ground. On the 30th of June, 1908, herders in central Siberia looked up and saw a second sun crossing the sky. Then the world hit them. The blast knocked people off their feet more than 40 miles from the centre. A trading post far from the site had its windows blown in. Witnesses described a heat so intense they thought their shirts were burning. The sound rolled across the region, and pressure sensors in England thousands of miles away registered the wave hours later. Seismographs in distant countries recorded the shock as though an earthquake had struck. In the days that followed, night skies across Europe glowed strangely bright enough that people in London reportedly read newspapers outdoors at midnight. Dust thrown into the upper atmosphere was catching sunlight from beyond the horizon. Nobody in Russia went to look for years. The region was almost impossibly remote. The country was heading toward revolution and war, and the accounts came from scattered communities far from any scientific institution. An expedition finally reached the area in 1927, nearly 2 decades later. What the team found was a forest laid flat across an area of roughly 800 square miles. Millions of trees knocked down, all pointing outward from a single centre, like spokes on a wheel. At that centre, the trees were still standing, stripped of branches and bark, burned but upright. That detail was the key to everything. Trees standing at the middle of a blast zone means the force came from directly overhead, pressing straight down, with nothing to push them sideways. Move outward from that point and the pressure wave arrives at an angle, toppling everything away from the centre. The team searched for a crater and found none. They kept searching for years. There was no impact scar because nothing solid ever reached the ground. The object, probably a stony body somewhere in the range of 150 to 200 feet across, had come apart in the air. Here is why that happens. An asteroid entering the atmosphere at those speeds experiences enormous pressure on its leading face, while the back stays comparatively untouched. That difference tears it apart. Fragments spread sideways, exposing more surface area, which increases drag, which increases pressure, which shatters it further. The disintegration runs away with itself in a fraction of a second, and the entire kinetic energy of the object converts to heat and blast several miles up. Estimates put the energy released in the range of many megatons, hundreds of times the Hiroshima bomb. The object was small by the standards we have been discussing, well under the 460-foot threshold. It never touched the surface. It erased a forest the size of a large city and its suburbs. Siberia in 1908 was one of the emptiest inhabited places on Earth. Shift the timing of that arrival by a few hours, and the planet's rotation would have placed a European capital under the same patch of sky. For 100 years, that event stood alone as the modern reminder of what falls from space. Then one morning in 2013, a rock came in over Russia again, and this time millions of people were awake, driving to work with cameras running on their dashboards. It arrived at 9:20 in the morning, local time, over the city of Chelyabinsk, and the first thing anyone knew about it was that the sky had turned brighter than the sun. Russian drivers keep dashboard cameras running as a matter of habit, which is why this is the best documented arrival in history. Dozens of angles, ordinary streets, morning traffic, and then a light so intense it casts hard shadows across the snow and washes out the video. The object was around 65 feet across. Small. A house-sized lump of stone weighing perhaps 10,000 tons, travelling at roughly 11 miles per second. It entered at a shallow angle, which meant a long path through the atmosphere and a long, spectacular trail. For several seconds it drew a line of fire across the sky, shedding fragments, brightening as it went. Then, about 18 miles up, it came apart. The videos catch a specific and horrible detail of physics. The flash comes first. People stop their cars, get out, film the smoke trail, point at the sky. Then roughly 2 minutes later the sound arrives, and with it the pressure wave. Sound travels through air at about 1/5 of a mile per second. Light does not wait. That gap between seeing and hearing is why so many people were standing at their windows staring upward when the blast reached them. Glass shattered across the city and beyond. Around 7,000 buildings suffered damage. A factory roof partially collapsed. Roughly 1,500 people were hurt badly enough to seek medical help, and the overwhelming majority of those injuries came from flying glass from windows they were looking through at that exact moment. The energy released has been estimated at around 30 times the Hiroshima bomb. Every bit of it dumped into the air miles above the rooftops. Now here is the part that reframes the whole chapter. Nobody saw it coming. There was no warning of any kind, no alert, no tracking, no name in a catalogue. The first detection of that object by any human being was the flash itself. And the reason is almost insultingly simple. It came from the direction of the sun. Astronomers reconstructed its path afterward and found it had approached Earth from the daylight side, moving in from a region of sky that ground-based telescopes physically cannot observe. To see an asteroid, you need it lit by sunlight against a dark background. An object approaching out of the sun's glare is lit from behind, drowned in scattered light and invisible. Optical telescopes work at night. Objects that arrive from sunward arrive unannounced. That same year, an even more famous asteroid was making a close, well-predicted pass by Earth, and observatories worldwide had scheduled time to watch it. The Chelyabinsk object was completely unrelated, arriving on a different trajectory hours earlier. The world was watching one rock while another one hit us. So the observatory in Chile, for all its power, inherits the oldest limitation in the trade. It sees only the night side. It cannot look at the sun, and it can barely look near it, which means there is a permanent hole in our coverage, shaped like a cone, pointed straight at the one object that lights everything else up. And something is already being built to fly into that blind spot and look back at us. There is a cone of sky above your head that no telescope on this planet can search, and it moves with the sun. Every optical observatory on Earth works the same way. It waits for darkness, then looks outward at objects lit from behind us, glowing against a black background. That arrangement fails completely for anything sitting between us and the sun. Such an object shows us its unlit side, drowned in glare, hidden inside the brightest thing in the sky. Astronomers can nibble at the edges. During the last minutes of evening twilight and the first minutes of morning twilight, surveys sweep low along the horizon, grabbing whatever they can from the narrow band of sky the sun has just left or is about to enter. Those hurried scans have turned up a rare category of asteroid whose entire orbit sits inside Earth's, objects that never appear in the night sky at all. They exist, we know that much. How many exist stays an open question, because we can only glimpse them in the few minutes each day when conditions allow. Everything else in that cone remains unknown until it arrives. The only real fix is to stop looking from here. About 1 million miles sunward of Earth sits a balance point where the gravity of our planet and the gravity of the sun combine in a way that lets a spacecraft hover, keeping pace with us as we orbit. Park a telescope there, and it gains a vantage no mountain can offer. It can look sideways and back toward Earth's path, watching the region that our night sky can never cover. 2 projects aim at this problem. The American mission, an infrared telescope with a mirror about 20 inches across, is scheduled to launch no earlier than September of 2027. It hunts in heat rather than visible light, which matters enormously, and it will operate from that balance point out ahead of us. A European mission is being designed specifically to stand watch in the sunward direction, aiming to spot incoming objects of concerning size, while there is still time to warn anyone. The infrared part deserves attention. An asteroid in space absorbs sunlight and re-radiates it as heat, and heat does something reflected light refuses to do. It reveals the objects that are dark. A charcoal-coloured rock reflects almost nothing, which makes it nearly invisible to a normal camera. That same rock absorbs almost everything, which makes it warm, which makes it glow brightly in infrared. The very asteroids that hide best from ordinary telescopes shine hardest in heat. So the strategy taking shape has 2 halves. A gigantic camera on a Chilean mountain sweeping the night sky over and over, catching the enormous population that comes out after dark, and smaller, colder eyes in space, staring into the glare where the ground cannot follow. Neither one covers the whole problem alone. there is an obvious question hanging over all of this effort, and it is fair to ask it bluntly. Suppose the system works. Suppose one of these machines finds a rock with our name on it. Then what? The honest answer is that we found out sooner than anyone expected, and it happened by accident. 2 days after Christmas in 2024, a survey telescope in Chile logged a faint moving dot. Routine, unremarkable, one of thousands that month. Within weeks, that dot had climbed to the top of every risk list on Earth and triggered the first coordinated planetary defense response in human history. The discovery came 2 days too late, in a specific and telling way. When a survey telescope in northern Chile picked up the object on the 27th of December 2024, the rock had already made its closest approach to Earth. It had come in, swung past, and started leaving before anyone on this planet noticed it. It had approached from the daylight side. Given the name 2024 YR4, it measured somewhere between 170 and 220 feet across. A stony body roughly the width of a football field is long, tumbling away from us at thousands of miles per hour. Automated systems flagged it immediately, because the software that watches every new discovery runs the orbit forward and checks for intersections with Earth. This one produced a hit, a small chance of impact on the 22nd of December, 2032. Small chances are common. They almost always evaporate. Here is why. A newly found asteroid has been observed over a handful of nights, which means its orbit is a fuzzy estimate rather than a fixed line. Project that fuzz forward 8 years, and the possible positions spread into an enormous cloud. If Earth happens to sit inside that cloud, the software honestly reports a non-zero probability. Then astronomers gather more observations, the fuzz tightens, and the cloud usually shrinks away from us. This one did the opposite. Through January, follow-up observations came in, and the probability climbed. 1%, then 2%, then higher. By early February it reached roughly 3%, about 1 chance in 32. That figure sounds low until you compare it to history. It became the highest impact probability ever recorded for an object of that size or larger. On the scale astronomers use to rank asteroid threats, it climbed to level 3, a rating that calls for public attention. Something else happened, quietly, that mattered more than the number. The international machinery activated, a global network for asteroid warning coordinated observations across the planet. A separate international group tasked with planning what governments would actually do about a confirmed threat began meeting on this specific object. Both bodies had existed for years. Neither had ever been triggered by a real case. Telescopes across 4 continents pointed at one faint dot. Astronomers dug through archived images hoping to find it in older photographs, because a sighting from years earlier would anchor the orbit enormously. Time was short in a particular way, since the rock was speeding away and would soon become too faint for anything to follow. Then the largest infrared telescope ever launched turned toward it, out at its station 1 million miles from Earth. Those observations, combined with everything gathered from the ground, finally tightened the orbit enough to answer the question. By March of 2025, an Earth impact in 2032 was ruled out. Further work pushed the odds for the coming century down to essentially 0. The whole episode lasted about 10 weeks. It ended with relief, a mountain of new data, and a planetary defense community that had just completed its first genuine fire drill. Except, the story refused to end there. The uncertainty cloud had shrunk. Earth had stepped outside it. Something else had not. Sitting 250,000 miles away, airless, unshielded, and directly in the remaining spread of possible paths was the Moon. Ruling out one impact revealed another, because the possible paths did not disappear. They narrowed onto a different body. By early 2026, the calculated chance that this rock would strike the Moon on the 22nd of December, 2032, had reached about 4%. 1 chance in 25. The American and European estimates agreed closely. 4% is a strange number to sit with. It is small enough to expect nothing, and large enough that serious people started running scenarios. Those scenarios were vivid. The rock would arrive at roughly 9 miles per second, which works out near 31,000 miles per hour. With no atmosphere to slow it, nothing would burn away, nothing would break up in flight. the full object would meet solid ground at full speed. The energy released would be equivalent to several million tons of high explosive. The crater carved out would measure something like 0.6 of a mile across. For the Moon, that is ordinary business. Its surface records billions of years of exactly this treatment. For us, it would have been the most spectacular event in the sky in modern history. The impact flash would likely have been visible from Earth, and the strike would have happened on a date when a large portion of the planet could watch. Then researchers looked at the debris. An impact that size throws material outward at enormous speed, and the Moon's gravity is weak. A fraction of that ejected rock would escape entirely, spilling into the space between the Moon and Earth. Presentations at a scientific meeting in late 2025 put a rough figure on the follow-on risk. Something around 1 chance in 100 that the strike would scatter a swarm of small fragments into the region where our satellites operate. Thousands of spacecraft live in that region. So do astronauts. Small fragments moving at orbital speeds are a genuine hazard, and a sudden cloud of them arriving without warning would be an unprecedented problem. There was one more complication, and it was maddening. The asteroid had already faded. By the spring of 2025, it had travelled far enough that even the most powerful instruments could no longer see it, and it would stay invisible until roughly 2028. The 4% figure looked frozen in place for years. Then a team went back to the Great Infrared Telescope in space and asked for 2 more looks. In February of 2026, on the 18th, and again on the 26th, it found the asteroid. Faint, distant, at the very edge of what the instrument could manage. Those 2 observations were enough. With the new data folded in, the orbit sharpened dramatically. The spread of possible positions for that December date collapsed, and the Moon fell outside it. The rock will pass the lunar surface at a distance of about 13,200 miles. Impact ruled out. The story closed for good. Look at what actually saved the situation in both acts. No spacecraft launched, no rocket flew, no one pushed anything. The entire response consisted of pointing instruments at a dot and measuring it more carefully. That worked because there were 7 years of margin. Information had time to arrive. Which points at the hardest truth in this whole field. Against an incoming asteroid, the most powerful weapon humanity possesses is nowhere near as important as how early we notice. Deflecting an asteroid sounds like a problem of power. It is a problem of scheduling. Start with the physical situation. An asteroid follows a path around the Sun set by its speed and direction. To make it miss Earth, you have to change that path. The obvious mental image involves shoving the rock sideways out of the way, like pushing a car off a road. That image is wrong, and the correct one is far more encouraging. You do not need to move the asteroid away from Earth. You need to change when it arrives. Both bodies are travelling. Earth sweeps along its orbit at about 66,000 miles per hour, which means our planet covers its own diameter in roughly 7 minutes. Change an asteroid's arrival time by a few minutes, and the collision becomes a miss. Speeding a rock up slightly, or slowing it slightly, gradually shifts it forward or backward along its own track. Give that shift enough orbits to accumulate, and a nudge becomes thousands of miles of separation. Here is the part that makes early warning everything. Suppose you change an asteroid's speed by a tiny fraction, roughly the pace of a crawling snail. Applied 20 years before the encounter, that change accumulates through 20 years of travel and moves the rock a great distance along its path. Applied 20 days before, it accumulates for 20 days and moves the rock almost nowhere. The effect of your push multiplies by the time remaining, so the difficulty of deflection does not scale with the size of the threat nearly as sharply as it scales with how late you find it. A large asteroid spotted 30 years out is a manageable engineering project. A modest one spotted 6 months out may be beyond anything we could do. This is why survey telescopes matter more than rockets. Every year of advance warning is worth an enormous amount of delivered force, and warning is cheap. Force is not. There is a second reason time matters, and it has nothing to do with physics. It takes years to build and fly a spacecraft. Designing a mission, constructing it, testing it, launching it, and cruising to a target measured in tens of millions of miles consumes most of a decade even when everyone moves fast. Add the political reality. Someone has to decide, fund, and coordinate the response across nations, and that process has never been rehearsed for real stakes. Stack those requirements and a rough answer emerges. To handle a threatening asteroid properly, you want to know about it at least 10 years ahead, and preferably several decades, which means the useful question is a survey question. How completely have we mapped the objects that could reach us, and how far ahead can we see them coming? For a long time, all of this remained theory, elegant arithmetic on a whiteboard, unproven in the real world, with no evidence that a spacecraft could actually alter the path of a body in space. Then, in the autumn of 2022, a probe the size of a vending machine flew toward a small moon orbiting an asteroid, aimed itself at the center, and made no attempt to slow down. The result surprised the people who planned it. The last images came back at a few frames per second, showing a grey landscape of boulders rushing up to fill the screen, and then the signal stopped. On the 26th of September 2022, a spacecraft weighing about 1,300 pounds struck a small body called Dimorphos at roughly 14,000 miles per hour. The target had been chosen carefully. Dimorphos orbits a larger asteroid named Didymos, circling it like a moon, and that arrangement solved a measurement problem. Detecting a small change in an asteroid's orbit around the Sun would take years of tracking. Detecting a change in a moon's orbit around its parent takes only careful timing of eclipses, since the pair regularly pass in front of each other from our viewpoint. Ground telescopes could measure the result within weeks. Before impact, Dimorphos completed a lap every 11 hours and 55 minutes. Mission planners set a success threshold of 73 seconds of change. Their best predictions clustered around 7 to 10 minutes. The measured result came in at about 32 minutes. The push had been 3 to 5 times stronger than the raw momentum of the spacecraft could explain. The reason lies in what the crash threw off the surface. Slamming into loose rocky ground, excavates material and flings it outward at high speed. Every ounce of that ejected debris leaves in the opposite direction, and by the same principle that drives a rocket, the escaping mass pushes back on the asteroid. The spacecraft delivered one shove. The plume of debris delivered several more. Telescopes watched a tail of dust stretch thousands of miles from the asteroid over the following days, glowing in reflected sunlight, visible as a comet-like streak. The mission proved the concept works. It also proved the outcome depends heavily on the asteroid you happen to hit. That amplification came from loose surface material available to be excavated. A dense, solid, metallic body would behave differently, absorbing the blow with far less thrown debris and far less bonus push, which means predicting how a real threat would respond requires knowing what it is made of before you launch. That knowledge does not come from a single visit. It comes from surveying huge numbers of asteroids, measuring their colours, their densities, and above all how they spin, because spin reveals internal strength in a way nothing else does from a distance. A telescope that photographs millions of rocks repeatedly, in multiple colours, over 10 years, becomes the instrument that tells us which asteroids can be pushed and which will crumble. Before we get to what those measurements revealed, there is one more rehearsal coming, and this one arrives on schedule without anyone launching a thing. In April of 2029, a rock wider than the Empire State Building is tall will pass closer to Earth than our own communication satellites, and roughly 2 billion people will be able to watch it cross the sky without a telescope. On the 13th of April, 2029, a Friday, people across Europe and Africa will look up and see a star that moves. The object is called Apophis, and it measures roughly 1,100 feet across. Stand it on end beside the tallest building in a major city, and it would loom over the skyline. It will pass within about 20,000 miles of Earth's surface. That distance deserves a comparison because it sounds enormous, and it is not. Communications and weather satellites in the high geostationary belt orbit at roughly 22,000 miles. The asteroid will thread beneath them, closer to us than the spacecraft delivering television signals. An object that large coming that close happens perhaps once in several thousand years. When Apophis was discovered in 2004, early calculations produced a genuine scare. For a brief period, it held the highest impact rating ever assigned, with a small but real chance of striking Earth in 2029. Additional observations, including archival images found later, erase that possibility. Astronomers have since ruled out an impact for at least the next century, so the flyby is safe, and it is also a laboratory nobody had to build. Earth's gravity will grip the asteroid as it passes, and the pull on the near side will exceed the pull on the far side. That difference, stretched across a body 1,100 feet wide, applies real stress. Scientists expect the encounter to change how the rock tumbles. They suspect it may trigger landslides across the surface, shifting boulders, exposing fresh material that has been buried since the solar system was young. Some models predict small quakes running through its interior. Watching that happen would teach us more about asteroid structure than a decade of theory. So missions are being arranged. A European spacecraft is planned for launch in 2028, timed to arrive at the asteroid in February of 2029, ahead of the close pass. It will study the rock in detail before, during, and after the encounter, measuring exactly how a body of that size responds to a gravitational squeeze. An American spacecraft, originally built to collect samples from a different asteroid and still healthy after delivering its capsule to Earth, has been redirected. It will catch up with Apophis after the flyby and spend many months in orbit around it. Between them, we get a before and after portrait. The public side will be extraordinary in its own right. As it crosses the sky, the asteroid will shine at about the brightness of a middling star, moving fast enough that its motion is obvious to the naked eye. Estimates suggest around 2 billion people will be positioned to see it. Most of them will never have watched a solar system body move in real time. All of this rests on a single assumption, and it is worth naming. We know exactly where Apophis will be, to within a few miles more than 2 years out. That certainty came from decades of patient tracking after one early scare. For the vast majority of objects out there, we have nothing close to that. Building that certainty requires measuring rocks by the thousand, and when the survey in Chile started doing exactly that, one of the first things it found was a set of asteroids behaving in a way that should have torn them apart. Somewhere between Mars and Jupiter, a mountain of rock nearly half a mile wide completes a full rotation faster than you can boil an egg. It carries the designation 2025-45, and it turns once every 1 9/10 of a minute. Picture that scale properly. The object stretches roughly 2,300 feet across, about the length of 8 football fields laid end to end. A landmark that size in a city would take you 10 minutes to walk around. Now spin it. Sunrise to sunrise in under 2 minutes, a day and a night, over and over, faster than a traffic light cycle. It is the fastest rotating asteroid of that size ever discovered, and it surfaced in the very first batch of results from the new observatory. The discovery came from a specific advantage of the survey's design. During the initial test observations, the telescope photographed the same patch of sky repeatedly and rapidly, which meant many of these newly found rocks were captured more than 100 times each. That density of coverage unlocks a technique. An asteroid is rarely a smooth sphere. Most are lumpy, elongated, shaped more like potatoes than marbles. As such a body rotates, it presents alternately a wide face and a narrow face toward us, and the amount of sunlight it reflects rises and falls in step. Plot brightness against time and you get a wave. Measure the spacing between peaks and you have the rotation period, without ever resolving the object as anything more than a point of light. A team analysing those first images produced reliable rotation periods for 76 objects, and among them found 19 spinning at extraordinary rates. Alongside the record holder, others turned once every 1 9/10 minutes, every 3 8/10 minutes, every 13 minutes, every 16 minutes. All of them measured several hundred feet across or more. Before this, astronomers had found a handful of rapid spinners, mostly small objects in our own neighbourhood. Finding a population of them out in the main belt at these sizes opened a door that had been shut. The result appeared in the first peer-reviewed paper written from data taken with the great camera. Here is why any of this matters beyond curiosity. Spin is a structural test performed for free. Any rotating body experiences an outward tendency at its surface, the same effect that presses you against the door of a car taking a fast corner. Increase the spin rate, and that outward tendency grows sharply. For an asteroid, gravity is the only thing holding the outer material down, and asteroid gravity is pitifully weak. Stand on a 500-foot rock and a gentle jump would launch you off it permanently. So there is a rotation speed at which a loosely assembled asteroid can no longer hold itself together. Spin it faster and the surface simply leaves. Astronomers measured that limit long ago, across thousands of objects, and it sits at a rotation period of roughly 2 hours. These new discoveries are turning between 4 and 60 times faster than that, which means they are made of something the standard picture of asteroids does not allow. For most of history, people assumed an asteroid was a rock, one solid object, like a boulder, only larger. Spacecraft visits demolished that idea. When probes reached small asteroids up close and studied them properly, the measurements refused to add up. Scientists calculated each object's mass from how strongly it tugged on the passing spacecraft, then calculated its volume from images, then divided one by the other to get density. The answers came out far too low. Many asteroids proved considerably less dense than the rock they are made of. The only explanation is empty space inside. Large fractions of these bodies, sometimes 40% or more, consist of gaps. They are piles. Collisions over billions of years shattered the original bodies of the early solar system into fragments, and gravity gathered those fragments back into loose heaps. Boulders resting on boulders, gravel filling the cracks, held together by a gravitational grip so feeble that a firm push would scatter it. Missions to 2 of these objects confirmed the picture in dramatic fashion. One spacecraft sent to collect a sample touched a surface expecting solid ground and instead sank into it. Engineers described the material as behaving almost like a fluid, offering so little resistance that the probe would have kept descending had it not fired its thrusters to back away. The surface of that asteroid was closer to a ball pit than a landscape. This is where the 2-hour spin limit comes from. A pile of loose rubble held only by mutual gravity has a maximum rotation rate, and cross that line and material starts drifting off the equator, which returns us to the objects the survey just found. A body nearly half a mile wide turning once every 2 minutes cannot be a loose pile. The outward tendency at its equator would exceed its own gravity many times over. Every unattached fragment would fly away. So something else is holding these objects together. 2 possibilities lead the field. Some of them may be single coherent chunks, solid pieces of rock with genuine internal strength, survivors or fragments of larger bodies broken in ways that left them intact rather than shattered. Or there is cohesion. Fine dust between grains at extremely small scales can stick through weak electrostatic and molecular forces, the same reason flour clumps and powder cakes. Across an entire asteroid, that faint stickiness might supply just enough extra grip to hold a fast rotator together against the odds. Distinguishing between those options tells us something important about what the asteroid population actually contains. And it tells us something operational. If you ever have to move one of these objects, its internal structure decides everything. A solid body takes a hit and transfers the momentum through itself, moving as a unit. A rubble pile absorbs the blow differently, deforming, throwing out enormous quantities of debris and responding in ways that are far harder to predict. This survey is about to measure spin rates for millions of asteroids, which means it will map that structural divide across the whole population for the first time. There is a reason planetary defense researchers care so intensely about this distinction. Hit the wrong kind of asteroid too hard, and you do not deflect it, you multiply it. An asteroid you can move is a problem solved. An asteroid you accidentally split is a problem multiplied. Consider what a strong impact does to a loosely bound heap of rubble. The energy arrives at one point and propagates outward through a body with almost no internal strength holding it together. Instead of accelerating as a single object, the pile can come apart. Now, in place of one incoming rock on a known path, you have many fragments on slightly different paths, spreading over the years that follow. Some of those fragments miss, some may not. Instead of one large impact in one location, you could produce several smaller ones spread across a wider area, arriving over hours or days. Depending on the sizes involved, that outcome ranges from an improvement to a catastrophe. This is why planetary defense studies obsess over gentleness. The crash test in 2022 worked partly because the target absorbed the blow and stayed intact, and partly because the debris it threw off happened to enhance the push. Both outcomes were desirable. Neither was guaranteed in advance, and researchers admitted openly afterward that the strength of the effect exceeded their models. Follow-up observations showed that the impact reshaped the target's surface considerably, and one study of the aftermath tracked boulders flung outward with enough energy to matter on their own. The lesson landed clearly. Kinetic impact works, and it works with a margin of unpredictability that scales with how little you know about the target. Alternatives exist for exactly this reason, and most of them trade speed for control. One concept parks a heavy spacecraft near an asteroid and simply hovers there for years. The spacecraft's own gravity, feeble as it is, tugs the rock continuously, and over a long enough period that whisper of attraction alters the orbit measurably. No contact, no debris, no risk of shattering anything. The catch is that it takes years, sometimes decades, to accumulate a useful change. Another approach heats one side of the asteroid, whether by concentrated sunlight, lasers, or a nearby energy release, so that vaporized surface material jets away and acts like a weak thruster. Gentler than a collision, slower than a collision, and again demanding an enormous head start. Every option on the table converts warning time into safety, which brings the argument full circle in a way that keeps repeating in this field. Detection is the whole game, because detection is what buys the years that let the gentle methods work. And detection has a hidden problem underneath it, one that shaped the entire response to that near miss on the risk list. When astronomers found that rock and started calculating what an impact would do, they could state its orbit with growing precision. They could state its arrival date to the second. They could not state its size. Their estimates spanned a range wide enough to cover completely different outcomes on the ground, and closing that gap required the most powerful telescope humanity has ever put into space. The reason is a piece of physics that fools every optical telescope ever built. A telescope measures how bright an asteroid appears. It has no way to know why. Two objects can produce identical dots. One is small and pale, reflecting a generous share of the sunlight that strikes it. The other is large and sooty, reflecting a sliver. From millions of miles away, both look exactly the same. The fraction of light a surface bounces back is called albedo, and among asteroids it varies enormously. Bright stony bodies can return around a quarter of the light hitting them. The darkest carbon-rich objects return 3 or 4%, blacker than fresh asphalt. That spread means brightness alone leaves you guessing about diameter by a factor of 2 or 3. For scientific curiosity, that vagueness is tolerable. For planetary defense, it is close to disqualifying. Impact energy scales with mass, and mass scales with the cube of diameter. Double the width of an asteroid and it carries roughly 8 times the punch. An object at the low end of an uncertain size estimate might break windows across a district. The same object at the high end could level a metropolitan area. Same dot in the telescope. Completely different evacuation plan. Which explains why the response to that rock on the risk list leans so heavily on infrared observations from space. Heat solves the illusion. An asteroid absorbs whatever light it fails to reflect, warms up, and radiates that energy back out as infrared. A dark object absorbs nearly everything, so it runs warmer and glows strongly in heat. A bright object reflects more and stays cooler. Measure both the reflected light and the emitted heat, and the ambiguity collapses. The two readings pull in opposite directions, and only one combination of size and reflectivity satisfies both. Infrared observations of that particular asteroid narrowed it to somewhere between roughly 170 and 220 feet across, and revealed a surface consistent with the stony body. That measurement mattered for every calculation that followed. The problem is that infrared astronomy is difficult from the ground. Our atmosphere glows in those wavelengths, and so does the telescope itself, and so does everything around it. Doing this properly requires cold instruments in space, which is precisely why a dedicated infrared asteroid hunter is being readied for launch. Meanwhile, the survey in Chile attacks the same problem from a different angle. It photographs every object through 6 different color filters, and the pattern of brightness across those colors carries information about surface composition. Colors will not deliver exact diameters. Across millions of objects, they will sort the population into families, flag the unusually dark ones, and tell follow-up missions where to point. So the emerging system has a division of labor. One machine finds nearly everything and characterizes it roughly. Another machine measures the dangerous ones precisely. Everything discussed so far has stayed close to home, inside the region where sunlight is still generous. The same 6 weeks of test observations that produced 11,000 asteroids also reached out to the freezing edge of the solar system, past Neptune. where objects are so distant and so dim that our entire catalogue of them fits in a modest spreadsheet. The survey added hundreds in a month and a half. 2 of them were travelling on orbits so stretched that they raise questions about what else is out there. Beyond Neptune, sunlight arrives so weakly that noon looks like deep twilight and everything is made of ice. This region holds the leftovers of planet formation, bodies that never merged into anything larger and have circled quietly ever since. Pluto is the famous resident. Thousands of smaller objects share the neighbourhood. Cataloguing them has been slow, difficult work spanning about 3 decades since the first one turned up in 1992. These bodies sit billions of miles away. They reflect faint sunlight off dark icy surfaces, and they crawl across the sky so slowly that distinguishing them from stars takes patient repeated imaging. In 6 weeks, the new survey found roughly 380 of them. That single haul added around 8% to the entire outer solar system census, assembled over 30 years by everyone else. Over the full decade, projections suggest the number of known objects out there will increase by close to a factor of 10. 2 of the new discoveries stood out immediately. Both travel on orbits that are enormously large and dramatically stretched, swinging from the outer solar system to distances that dwarf the planetary region before falling back. Objects like that are prizes, because their paths are shaped by whatever gravitational influences act on them at those distances. Read enough of them, and you can infer what is out there. This is the same category of evidence that fuels the long-running argument over whether an undiscovered planet lurks in the far reaches of our solar system. That idea grew from a small sample of distant objects whose orbits appeared to cluster in a suspicious way, as though something massive were shepherding them. The sample has always been the weakness. With only a handful of objects, coincidence remains a live explanation, and critics have pointed out that the way we search introduces its own biases toward finding certain orbits. Expanding the census by a factor of 10 changes the nature of that debate entirely. Either the clustering survives in a much larger sample or it dissolves. There is a second reason these icy bodies matter. They are the least altered material available to us. Out there, temperatures hover a few tens of degrees above absolute zero, and the ices that formed alongside the planets have never been cooked away. Their compositions are a record of what the young solar system was made of, and how that material was distributed before the giant planets shuffled everything. Reading hundreds of them, sorted by colour and distance and orbit, turns a scattering of anecdotes into a history. All of this came out of preliminary data, gathered while engineers were still tuning the machine. And buried in those same commissioning images was an object that belonged to none of these categories. It was not from the belt between Mars and Jupiter. It was not from beyond Neptune. It was not bound to the Sun in any way at all. It was passing through on a path that will carry it back out into the galaxy forever, and the telescope photographed it repeatedly before a single person on Earth knew it existed. On the 20th of June, 2025, on the first night of its science validation observations, the telescope happened to point at a patch of sky containing an object that had no name. Nobody noticed at the time. The image went into the archive with everything else. Over the following days, the same object appeared again and again. 9 separate detections between the 21st of June and the 2nd of July, gathered without anyone realizing what they had. On the 1st of July, a different survey announced a discovery. A comet on a path that made no sense for a resident of our solar system. Ordinary comets loop around the Sun on closed orbits, however long and stretched. This one was travelling too fast to be bound. It had entered the solar system from outside, would swing around the Sun once and would leave forever. It became the 3rd confirmed object from another star system ever identified, following one in 2017 and another in 2019. Once the announcement went out, researchers went back through the new observatory's archived images and found it sitting there, 10 days before the official discovery. The object came close to being named after the observatory instead. What Rubin's images showed was scientifically valuable in its own right. The comet already displayed a coma, a hazy envelope of dust and gas driven off its surface by sunlight, meaning it had begun to wake up on approach. Analysis showed something else that mattered for the future. Had the automated processing pipelines been running in real time on that data, there were enough observations to have flagged the object independently as a moving body. The system would have caught it on its own. The visitor itself deserves a moment. Its solid core measures roughly 0.6 of a mile across. It travels at about 140,000 miles per hour relative to the Sun, which is fast even by the standards of things falling through our neighbourhood. That velocity is a clue about age. Objects wandering the galaxy get gravitationally jostled by every star system they pass, and those encounters build up speed over time. A high velocity suggests a very long journey. Estimates place this object's age at 7 billion years or more, possibly beyond 10. Our Sun is about 4.5 billion years old. That chunk of ice was already ancient when our solar system began forming. It was born around another star, ejected by some gravitational accident, and has drifted between the stars ever since, crossing distances that make our entire planetary system look like a speck. Now it has passed through, been photographed, been measured, and is on its way back out. 3 such objects in 8 years, all found essentially by luck, using instruments never designed for the job. The survey now running in Chile was designed for exactly this job, and the estimates for how many it might catch over its decade of operation vary so wildly that the answer, whichever way it lands, will teach us something profound about how common these wanderers actually are. Ask the researchers how many interstellar objects the survey will find, and you get an honest shrug wrapped in numbers. Published estimates range from around 5 to as many as 500 over the 10-year survey. One astronomer studying the problem summed up the uncertainty plainly, saying it could be 5 or it could be 500, and adding that finding none would itself be a fascinating result. That spread exists because the calculation depends on a quantity nobody has measured. How much material do star systems throw away? The reasoning behind expecting any at all is straightforward. When planets form, they do so in a crowded disk of debris, and gravitational interactions between growing worlds fling enormous quantities of leftover material outward. Our own solar system almost certainly ejected a vast number of icy bodies during its violent youth, and those objects are out there somewhere, drifting between stars. If every system does the same, the galaxy should be sparsely filled with orphaned rubble. Turning that idea into a prediction requires knowing the density of the population, and until recently we had 0 examples to calibrate against. Now we have 3, all found in 8 years, mostly by accident. 3 data points gathered with instruments that were never optimized for the task already suggest the population is larger than early pessimism allowed. A survey built for the job changes the sampling completely. It watches the entire southern sky every few nights, catches faint, fast movers, and publishes alerts within a minute. An interstellar object entering the inner solar system would announce itself in the alert stream while still inbound. That timing is the prize. Both previous visitors were found late, already past their closest approach, or nearly so, leaving astronomers scrambling for a few weeks of observations before the objects faded. Nobody had time to prepare anything. Catch one early, and everything changes. Every major telescope on Earth and in space could be scheduled in advance. Spectra could be gathered while the object was brightening. Its composition could be measured properly, revealing the chemistry of a planet-forming disk around a star we will never visit. If a single visitor arrives on a favourable trajectory, a spacecraft intercept becomes conceivable. Mission concepts already exist, waiting in storage for a target worth chasing. Consider what that would actually mean. Material from another solar system, formed around another sun, delivered into our neighbourhood free of charge. We have never held anything from beyond our own system except tiny grains embedded in meteorites. There is a broader point buried in this. The survey was built to study dark matter and dark energy on the largest scales imaginable. Its asteroid work was a secondary benefit. Interstellar objects were barely a footnote in the original planning, because when the project began, nobody knew such things existed. The instrument keeps finding categories of discovery its designers never listed, all of which describes a decade of extraordinary science, provided everything it finds turns out to be harmless. The uncomfortable question remains unanswered. This machine will publish millions of alerts a night about things that move and change. What happens on the night one of those alerts describes an object heading directly for us? The first 60 seconds would look exactly like every other alert. An object appears in a difference image. The pipeline packages its position, brightness, and colours, and pushes it into the public stream alongside millions of others. Filters around the world sort it. Software flags it as a moving body and routes it towards solar system processing. Over the following nights, the survey catches it again as it sweeps that region of sky. Positions accumulate. The tracks link together into a candidate orbit, and the whole set goes to the International Clearinghouse that maintains the master catalogue. Then the orbit gets projected forward, and the software that screens every new object for future encounters returns something other than 0. At that point, the machinery from 2025 activates, and this time, everyone involved has done it before. 2 independent centres, one in the United States and one in Europe, run the impact calculations separately using different software, which provides a check against any single error. A global network coordinates follow-up observations, directing telescopes across many countries toward the object, because more data points shrink the uncertainty cloud. Astronomers immediately begin searching archives. If the object appears in images taken years earlier, before anyone knew to look, the orbit becomes far better constrained overnight. The threat rating gets published on a public scale from 0 to 10. The survey itself has a role here beyond discovery. It carries a system for interrupting its normal schedule and pointing at urgent targets, and that system has already been tested in practice on the interstellar comet during commissioning. A machine that can drop everything and stare at one object within minutes is precisely what a real emergency requires. Beyond the astronomy, a separate international group exists to advise on what governments should do. That body reviews deflection options, timelines and mission possibilities, and reports upward. Everything after that stops being a science problem. The honest weakness in this chain lies in follow-up capacity. Discovery is about to become effortless while confirmation stays laborious. Every candidate needs additional observations from other telescopes to nail down its orbit, and those telescopes are limited, oversubscribed, and shared among thousands of researchers with other priorities. Flood that system with 100 times more objects and something has to give. Astronomers have been preparing for years, building automated follow-up networks, recruiting robotic telescopes, and writing software that can decide which objects deserve attention without a human in the loop. Amateur astronomers matter here too, in a way that surprises people. A well-equipped backyard observatory can track a moderately bright asteroid, and coordinated amateur networks have contributed real observations to real risk assessments. None of this has ever been stress-tested at full volume. It is about to be, because the survey has now formally begun, and the discovery rate that produced 11,000 asteroids in 6 weeks was the machine running at partial effort. At full effort over the coming year, astronomers expect this single telescope to hand us something no generation has ever received. 1 million asteroids in 12 months, matching everything humanity found in the previous 2 centuries. On the 30th of June, 2026, the survey officially started. 10 years of scheduled observing, roughly 1,000 exposures every clear night. Each patch of southern sky revisited about 800 times before the project ends. In the first year alone, researchers expect around 1 million new asteroids. Set that against the historical record. The first asteroid was found on the opening night of the 19th century, the 1st of January 1801, by a monk in Sicily who thought he had spotted a comet. For decades afterward, discoveries trickled in 1 or 2 at a time, each one a career highlight. Photography sped things up. Electronic detectors sped things up again. Automated surveys in recent decades pushed the annual rate into the tens of thousands. 225 years of accelerating effort produced roughly 1.5 million known objects. One telescope is expected to match that in 12 months. The consequences ripple outward in directions that have nothing to do with counting. Individual asteroids stop being interesting on their own and become entries in a statistical portrait. With a sample that large, researchers can trace families of fragments back to the collisions that created them, dating catastrophes that happened hundreds of millions of years ago by watching how far the pieces have drifted apart. They can map the gaps in the belt where Jupiter's gravity has cleared out anything that strays into the wrong rhythm. They can measure how sunlight itself slowly reshapes orbits, a subtle effect where a rotating asteroid radiates heat unevenly and gives itself the faintest continuous push. Across millions of years that WISPR delivers rocks from the main belt into our neighbourhood, and with a large enough sample, that delivery system becomes measurable rather than theoretical. For planetary defense, the census closes the gap that has defined the field. Completeness in the dangerous size range rises from around 40% toward roughly 70%, and roughly 90,000 additional near-Earth objects join the catalogue. Each one gets an orbit, and each orbit gets projected forward, and the answer for nearly all of them will be that they miss us for centuries. That reassurance has value. Naming the objects that pose no threat is how you find the ones that do. There is a strange emotional weight to this transition, and the astronomers involved have talked about it openly. One described the situation as an explosion of discovery without precedent in the history of the science. For 4 centuries, astronomy has been a discipline of scarcity. Telescope time was precious, targets were chosen carefully, and a single object could occupy a career. That era is closing. The constraint moves from gathering data to understanding it, and 10 years from now, when the survey finishes and the final archive of roughly 500 petabytes sits complete, we will possess something no civilization has ever had. A map of everything that moves near us. The question then belongs to whoever is holding it. Every night, on a ridge in Chile, a dome rotates and a machine begins photographing the sky in 40-second intervals until dawn. It will do this for 10 years. What accumulates from that routine is difficult to describe in ordinary terms, a record of the changing universe, deep enough to reach galaxies whose light left them when the cosmos was a fraction of its current age, and detailed enough to catch a lump of rock a few hundred feet wide drifting past Mars, both at once, in the same frames from the same instrument. The asteroids were never the main mission. The observatory exists primarily to measure how invisible matter bends light across the sky, and how the expansion of the universe has changed over billions of years. Those are the questions its namesake spent her career opening up. The rocks came along for the ride, and they may end up being the part that matters most to the people alive when it finishes. Because here is what the census actually delivers. For the entire span of human existence, our species has lived on a target without a warning system. Every impact in the geological record arrived unannounced. The forest flattened in Siberia, the windows shattered over a Russian city, and the far older strike that ended the age of the dinosaurs all happened to a planet with no idea they were coming. We are the first generation with the option of knowing. That is a genuinely new condition, and it is worth being clear about its limits. The survey will find most of what threatens us, and it will miss things. It cannot see the daytime sky. It will not catch a small object arriving on short notice. Some fraction of the population will stay hidden until other instruments join the search. Knowing is also separate from acting. Finding a rock decades in advance only helps if that warning is used, and using it requires spacecraft, budgets, international agreement, and the patience to spend a decade responding to something that has not happened yet. Those are choices rather than technical problems, but the sequence has to start somewhere, and it starts with looking. Think back to how this began. 10 hours of testing. A camera aimed at one crowded patch of sky by engineers who wanted to know whether their equipment worked. 2,104 objects nobody had ever recorded, 7 of them sharing our region of space, all of them present the entire time and simply unseen. That was the machine warming up. The astronomer this observatory is named for spent years measuring something everyone assumed she'd gotten wrong, and in doing so revealed that most of the universe is invisible to us. She never received the prize her work deserved. Her instrument is now doing the same thing on a smaller scale and closer to home. It is finding what has always been there. The sky above you tonight contains millions of moving objects. Most of them will never come near us. A handful, somewhere in that swarm, will eventually cross our path. For the first time, we are building the list.